Okay, so now we can go over our single sample tests concerning a single mean. So we have two different cases. So one is where our standard deviation for our population is known, and one is for when it's not known. So we can go over when it's known first. So say we have our random sample from a distribution where x1 through xn is our random sample with our mean of mu and our variance of sigma squared. So we have our hypotheses here. So our null hypothesis is that our mean for our population is equal to some value, and then our alternate hypothesis is that our mean is not equal to that value. And for reasonably large sample sizes, by our central limit theorem, we can say that we can assume that basically our sample mean is going to be a good estimator of our population mean. And so we can use that to write our equation here. So we have basically we need to solve for our test statistic z, which will be our mean minus our value that we're saying is the mean, divided by our standard deviation divided by the square root of n, our sample size. And so we can calculate this, and we need our value, our test statistic, to lie within our interval negative z, where negative z alpha divided by 2 and z alpha divided by 2. And so if it lies within it, then we fail to reject, and if it lies outside of this interval, we reject. And it might be a little bit clearer to see here. So here's our interval, and here's our negative z alpha divided by 2 and our positive z alpha divided by 2. And so this is basically our two tails. So this is why it's called a two-tail test. And these are our two tails of our probability distribution, and if it doesn't lie within this big range here, and if it lies outside, then we reject our null hypothesis. So it's when we test with our hypothesis, where our null hypothesis is mu is equal to some value, so our mean is equal to some value, and then our alternate hypothesis is not equal to some value. That's how we know it's a two-tailed test, because it could be less than our value or it could be greater than our value. So we don't know which. So we can compute our test statistic, z equals mean minus our value for the mean, for what we're thinking might be the mean, divided by our standard deviation divided by the square root of our sample size. And so we reject our null hypothesis if the absolute value of our test statistic is greater than z alpha divided by 2. So that's basically the same thing as if it's outside of this range. Or we could also write it like 2 times the probability that z is greater than the absolute value of our test statistic, and then if that's less than our alpha value. And we multiply by 2 here just because it's a two-tailed test, so this is our probability for both sides both tails of our distribution. And so if it's less than our significance value, then it's very, very unlikely to happen with our null hypothesis, so we can reject our null hypothesis. So tests of one-sided hypotheses have the same test statistic, except the only difference is that our rejection region is only one tail of our distribution. So if we have our alternate hypothesis is that our mean is greater than this value, then we can compute the same test statistic, but we reject our null hypothesis only if z is greater than our alpha value, or if the probability of z being greater than our test statistic is less than our alpha value. And then alternatively, if our alternative hypothesis is that the mean is less than our value, then we reject if z is less than negative z of alpha, or if probability of z being less than our test statistic is less than our significance value. That might have been a little confusing, so we can go through an example. So I can go through this on my iPad in case that helps. Let me pull that up really quickly. Okay. Okay, so our question says, a random sample of 100 recorded deaths in the United States during the past year showed an average lifespan of 71.8 years, and we assume the population standard deviation of 8.9 years. And we're interested in testing in whether we have evidence that the mean lifespan is greater than 70 years. So the first thing we need to do is write our null and alternate hypotheses. So our null hypothesis H0 is that our mean is 70 years, and then our alternate hypothesis HA is that our mean is greater than 70 years because we want to test if it's greater than 70 years. And it doesn't give us an alpha value in this problem, but usually if they don't give you an alpha value, we can assume that it will be 0.05, so 5%. It's a common alpha value that's used. Okay, and then we can now calculate our z value. So we have our formula for our z value over here, so we can just use that. So we have our sample mean. So in our random sample, we have our mean, our average lifespan is 71.8 years, so that's 71.8. And then we can subtract what we're estimating our mean, our population mean to be, and that's 70 years. And then we have our standard deviation, so our population standard deviation is given in this problem, so that's 8.9. And then we have our sample size is n equals 100, so we can just do the square root of 100. And if we solve this, we should get 2.02. And then now we can check our probability. So if we calculate the probability of z being greater than 2.02, and we can use our z table for this, and we should get that it's equal to 0.0217, and then because this value is less than our alpha value, because our alpha value here is 0.05, then we can reject our null hypothesis. So we can reject H0, and so we have statistically significant evidence that the mean lifespan is greater than 70 years. Okay, and then now we have our t-test next, So our t-test is a test we use if our standard deviation is unknown. So let x1 through xn be our random sample from a normal distribution where both our mean and our variance is unknown. And then we can recall our function, or how to calculate t, which is really similar. So essentially we use the same formula, but we replace our standard deviation with our population standard deviation with our sample standard deviation, since it's a decent estimator of our population sample standard deviation. But since it's not the most accurate, we have to use our t variable instead of z, and we use a t-table for this. So if it's normal with our mean and variance, so we can test with our null hypothesis, mu, our mean is equal to some value, and our alternate hypothesis is that our mean is not equal to the value, and then we can compute our test statistic t, and that is our formula from before, where we have our sample mean minus our value that we think that the population mean might be, that we're testing for, and then divided by our standard deviation divided by the square root of our population, or our sample size n. And so we reject our null hypothesis if our absolute value of t is greater than t alpha divided by 2, with our degrees of freedom n minus 1, or equivalently we reject it if we can also write it in this form where it's 2 times the probability that t n minus 1, so t with degrees of freedom n minus 1, is greater than our absolute value t, of our test statistic t, and then if that's less than our alpha value or significance value alpha. And again, we have our times 2 here because it's a two-tailed test, and if it's not a two-tailed test, we wouldn't have our 2. So if we're testing for this, for if it's our single-tailed test where the mean is greater than the value, we reject if t is greater than alpha, t of alpha, and then we reject if, which is the same thing as the probability of t with degrees of freedom n minus 1 is greater than t, and then we check if that's less than alpha, and then it's the opposite for if our mean is less than our value, and yeah. So this might be a little confusing, so you might want to review it. It should be on your cheat sheet. Basically, as long as you know, as long as you can know how to use these formulas, you should be good. Yeah. So let's go through an example. We can do this on my iPad again. Okay, so it is claimed that a vacuum cleaner uses an average of 46 kilowatt hours per year. Suppose a random sample of 12 homes included in a planned study indicates that the vacuum cleaners use an average of 42 kilowatts per year with a standard deviation of 11.9 kilowatt hours. Does this suggest that at a 0.05 level of significance that the vacuum cleaners use on average less than 46 kilowatts hours annually, and we can assume that our kilowatt hours population to be normal. So here we're given our significance value. So let's just start with our hypotheses. So H0 is our null hypothesis, and so that's that our mean is 46 kilowatt hours. So we're using 46 because this is what is being claimed, so that's what the value we use for our null hypothesis. And then HA, since we're looking for if it's less than 46 kilowatt hours, it should be our mean is less than 46. And then we were given our significance value here, so that's 0.05. And then now we need to calculate our t statistic. So t, and so we have our formula over here. So it's equal to our sample mean minus our value divided by our standard deviation for our sample standard deviation divided by the square root of our population or sample size. N. So let's do that. So here we have the average is 42 given over here for our sample, and then we are looking for if it's equal to or less than 46, and then we have our standard deviation of our population is 11.9, and then our sample size is 12 homes, so that should just be the square root of 12, and that is equal to negative 1.16. And then now we can calculate our P. So our degrees of freedom is n minus 1. So our degrees of freedom is n minus 1. And that's important for when we're looking up in the t-table. So n here is 12, so 12 minus 1 is 11. So now we need to find the probability that our t with degrees of freedom 11 is less than our test statistic, which is negative 1.16. And if we just look that up on the t-table, you should find that this equals 0.135. And then since 0.135 is greater than our alpha value, which is 0.05, we fail to reject our null hypothesis. And so we can't accept our null hypothesis, but we can say that we don't have enough evidence to disprove our null hypothesis. Okay. And then, so when we test our null hypothesis, where our mean is equal to some value against our alternate hypothesis, where our mean is not equal to that value, at our significance value, or significance level alpha. So this is the equivalent to computing 100 times 1 minus our alpha level percent confidence interval on our mean, and rejecting our null hypothesis if our value for our population mean is outside of the confidence interval. So for example, in our z-test, we had this formula earlier where basically we calculate our test statistics in the middle, and then we check that it needs to be in between negative z alpha divided by 2 and positive z alpha divided by 2, and if it's within those bounds, we fail to reject, and if it's outside of those bounds, we reject our null hypothesis. And so if we rearrange those terms, we get this equation down here, and basically this is a confidence interval where our mean needs to be, our mean value that we're saying is our population mean, needs to be in between our sample mean minus this value and then our sample mean plus this value. And so it can be thought of as the values of our population mean, which yield a p-value greater than our alpha value. And so this is our hypotheses testing is the same as computing our confidence interval in this case. Though it should be noted that this equivalency is only holds true when both our hypothesis test and confidence interval are derived from the same method. So there are other ways to derive our hypothesis or to derive our mean value and like perform this task. So there are different ways to do this, and those will have different confidence intervals. So it's only for these two methods. Yeah.